Welcome to the Explainer. Today, we're not just talking theory. We are jumping right into the deep end. We're going to solve 10 classic physics problems step by step. So yeah, let's get into it. Think of this as a workout for your brain, right? We're going to tackle some really core concepts, break down exactly how to find the solutions, and just build up those problem-solving muscles. So, you ready to get started? And here it is. This is our source material, our challenge for today. It's a multiple choice quiz that covers everything from uncertainty and error all the way to dimensional analysis. We're going to work through these together. Okay, first up, we're tackling the absolute fundamentals. I mean, before you can do any of the cool advanced physics stuff, you have to know how to measure things properly. And, just as important, how to account for the errors that are pretty much inevitable. Before we dive into the problems, we've got to get this straight because these two terms get mixed up all the time: accuracy and precision. Think of it like this. Accuracy is all about hitting the bullseye, getting close to the real true value. Precision, on the other hand, is about consistency, hitting the exact same spot over and over, even if that spot isn't the bullseye. Getting this difference down is absolutely crucial for what's coming next. All right, here's our first problem. We're given a measurement, right? 0.50 millimeters plus or minus 0.02. That's our absolute uncertainty. And the question is, what's the percentage uncertainty? Hey, feel free to pause right here and give it a shot yourself before we walk through it together. The key to cracking this one is all in the formula. Just like our source shows, you take that absolute uncertainty, the plus or minus part, you divide it by the actual measurement, and then you just multiply the whole thing by 100. Simple as that. So let's plug in the numbers. We take our uncertainty, that's 0.02 millimeters, and divide it by the measured diameter, which is 0.50 millimeters. You multiply that result by 100, and bingo, you get exactly 4%. So the correct answer is B. All right, on to the next one. This time we're calculating percent error. This is a bit different. It's all about comparing your experimental result to what you expected to get. So again, it's a great chance to pause here and try to crunch the numbers yourself. So how do we solve it? Well, you find the difference between what you expected and what you actually got. Then you divide that difference by the expected value and finally multiply by 100. That gives us 9.9%, which means the answer is A. Okay, here it is, the classic accuracy versus precision test. So we have a known value. The standard is exactly 2 grams. But our scale keeps giving us the same weird reading, 7.32 grams every single time. So what does that tell us about this balance? Okay, so if we look at our solution guide, it says the correct answer here is C, accurate but not precise. But let's take a closer look at the reasoning behind that. And this is why you always have to read critically. The source says the answer is C, but look at its own explanation. It says the reading is far from the true value. That's inaccurate. But everyone gets the same reading, which means it's precise. So the explanation is actually describing option D, precise but not accurate. It's a great reminder to always think through the logic yourself, because sometimes even the source material can have a little slip-up. In fact, if we look ahead to the source's own explanation for a different question, it defines precision exactly as we just discussed. Repetition gives the same result. This lines up perfectly with what happened in question 3, where everybody got 7.32 grams, so it's definitely precise. Okay, let's jump ahead to question 6. This time, we have a whole set of measurements, and we need to figure out the uncertainty from the data itself. How do we even do that? Well, the source suggests a really simple and practical method here. Just find the range of the data. You take the highest value, which is 3.4 seconds, and you subtract the lowest value, 2.8 seconds. The difference is 0.6 seconds, and that gives us a good estimate for our uncertainty. So the correct answer is B, plus or minus 0.6 seconds. All right, let's switch gears and move on to round 2. We're going to see how these ideas build into an incredibly powerful tool called dimensional analysis. This is less about specific numbers and more about the fundamental nature of physical quantities themselves. It's really cool stuff. So what is dimensional analysis? Well, you can think of it like a fundamental grammar check for any equation in physics. Every single physical quantity can be broken down into some combination of mass, length, and time. And here's the magic. If the dimensions on one side of an equation don't match the dimensions on the other side, the equation is just plain wrong. It's that simple and that powerful. So, our first challenge in this round is to find the dimensions of big G, the universal gravitational constant. The famous constant from Newton's law of gravitation.
So how in the world do we figure that out? Well, we start with Newton's famous formula, right? Force equals g times mass 1 times mass 2, all divided by the distance squared. All we have to do is rearrange that formula to solve for g, and then we substitute in the known dimensions for force, mass, and length. It takes a little bit of algebra, but it gets us to the right answer, m to the minus 1, L cubed, t to the minus 2.
Okay, and for our last problem in this round, we're going to use dimensional analysis in reverse. Instead of finding the dimensions of a constant, we're going to use dimensions to check which one of these formulas for the speed of ocean waves could actually be physically correct. Let's put option A to the test. V equals the square root of lambda times g. So, on the left side, we've got speed, or v. The dimension of speed is just length over time, or LT-1. Easy enough. Now for the right side, we have the square root of wavelength. That's a length, so L, times g, which is acceleration. That's LT-2. That gives us the square root of L squared t to the minus 2, which simplifies to, wait for it, LT-1. They match. The dimensions on both sides are the same, so it's a valid formula. All right, you ready? Time for the final boss. It's just one quick question to go, this one focusing on the concept of order of magnitude. And here it is. What is the order of magnitude of 10 to the power of 6 plus 10 to the power of 3? Now, this is an interesting one. The source gives the answer as A, 10 to the 9th, and its reasoning is that the result is dominated by the larger term, which is 10 to the 6th. But hold on a second. 10 to the 6th is a million. 10 to the 3rd is 1,000. A million plus 1,000 is 1,001,000. That's really close to a million, which is 10 to the 6th. So the order of magnitude should be 6. The source's answer of 9 might come from accidentally adding the exponents, which is a super common mistake and a great reminder to always double-check your own work. And that's a wrap on our problem set. Phew, we've covered a lot of ground. So let's take a second to recap the essential skills we've sharpened today. What's in our new problem-solving toolkit? So today we went over how to calculate both percentage uncertainty and percent error. We really hammered home that critical difference between accuracy and precision. We got to use the power of dimensional analysis to check if formulas are valid and even to figure out the dimensions of constants. And finally, we saw a really practical way to estimate uncertainty just from the range of a data set. These are all absolutely indispensable tools. Which leaves us with one final big picture thought. We've seen how these basic principles work on paper, but think about the real world for a second. From building massive bridges to launching rockets into space, how can these fundamental checks for error, for precision, and for dimensional correctness literally prevent catastrophic failures? It's a pretty crucial question to think about. Thanks for joining us on The Explainer.